So hello, I'm Kris, and welcome to NFPAC Element, a case study in which we'll take a look into different approaches towards getting a nth element out of a variadic pack. So I hope that sounds exciting. The talk is not about state nth element, so if you were looking forward to that, I will disappoint you, but I have some tricks here. There will be a lot of magic, so hopefully that will be even more exciting than NFPAC element itself. So what we'll be talking about. Firstly, we'll introduce the motivation, why we actually care about it, what it's about. We'll go as far as STD get implementation. So, after this talk, you will understand why STD tuple is the way it is and how it works under the hood and how we can improve it. We'll also compare it between different compilers, so the different approaches which we will explore, compare them between different compilers as well as different languages. So there will be a bit of Rust here and other languages which are trying to get on the stage. And we'll sum up the findings and all the study and see what was good, what was bad, and how we'll go about it in the future. So there'll be a lot of slides, a lot of code. Some of the good practices which I found important will be marked as with a dark blue background. So and that's something to take out of the talk. So that'll be good. And everything is powered by the Compiler Explorer. The links are always provided, and everything can be easily checked afterwards or during the talk. So without further ado, let's begin. So the motivation. I have to get that out of my chest. I wanted to point out that I'm working for the high frequency trading, so the performance is important for us. But why we care about template metaprogramming in general? I believe that as a digression, that on average, I think Rust implementation will be more performant than C++. I don't think that's a really controversial statement, but I think that's true. And the reason being is the fact that Rust just have better defaults. It's much harder to screw up. There's no move semantic by default. There's no IO streams by default and stuff like that. So it's I think it's easier on average to write C++ Rust code to be faster than C++ code. However, I think the main reason why we care about the C++ so much or we use it, especially in finance companies, is the fact that we have more ability to actually tweak the code to the levels that I think are unachievable at the moment by other compilers, other implementers. So, in other words, if you have the best code in Rust, like tweaked really to the ground, and the best C++ code, I would say the C++ code would win at the moment, because we have all these low-level abilities, as well as especially the better approach towards template metaprogramming, where we can do much more things. And the latter will be expressed here. And just to point out why it would be faster, because in my opinion, the faster way to do the computation is just by not doing it at all. And that's why we'll be talking about nth element, because that's the most common algorithm in the variadic pack which we have to implement to get things sorted. Obviously, there are trade-offs. C++ is slow to compile, so the fastest code we can get may depend on the compilation times, but that's why the exploration here. Okay, so I get that out. Sorry for the digression, but I think that's important as a motivation. The performance, reflection, and other things are also important, in my opinion, as a use case, because there are tons of use cases for reflection. One of them, and all of them, by default, if you want performance, will require static reflection. Static reflection will require some TMP, and it will require a tuple, and tuple will have elements, and we'll be able to get the elements and do all the reflection out of it. So having ability to easily operate on tuples is important for the reflection. The same for the serialization, if you want to JSON out of it, all the use cases which are propagated by the reflection, spread around. And there are tons of them, tons more, which are really important as well. So that's the motivation. If you have any questions, feel free to ask them during the talk. I will try to answer if I will see them. If not, I'll be available afterwards, so feel free to hold off. Okay, so the motivation, the simple motivation for the NPAG element, is that from the low-level code perspective is the fact that when you have a tuple, and you have a tuple from 1 to 3, that will be a tuple of end and end. If you get an end, that will be ambiguous because we don't know the first one, second one, the third one. However, if you get the nth PAG element here by using a number, that will give us the proper value. And if you get the one which just doesn't exist, that won't compile, it will give really bad error message. But that's the current state of C++. So let's not focus on that. Anyway, that will work with the numbers. That doesn't work with the types. That will also, kind of reflect the reflection proposal as well. Yeah, out of range. That's more or less what we would like. Not even close what we will get. So what are we now? I think Andrei Alexandrescu summarized that pretty well in a tweet recently about where we are now. He asked, what's the simplest way to get the nth element out of the PAG? That his solution. As you see, it's not an easy way, and it's important to get that right. C++ doesn't have really good facilities right now, and a lot of them are not compile friendly, and a lot of them are not user friendly. But as we will explore in the future, there are potential improvements which will be made to the language, which make that easier. Okay, so right now let's begin what we actually can do. And there are a lot of things which we can't do, and we'll see how we can work on that. But some things are quite easy in C++ at the moment. So getting the first element is actually easy. It's because the variadic parts are greedy. So in order to do so, we create a lambda and we pass args to it. And the first element is the one which we want to get, and rest, the auto ... we want to ignore. So in that case, when we have first PAG element 1 to 3, we will get the first element because we will get this overload being set to the first, and 2 and 3 will be in the auto ... and we return the first. So that's easy. That's just a lambda, immediately invoke lambda here. What we can else do? We can also take grab the last element easily. Unfortunately, we cannot do that with the variadic PAG function as we did before, because we cannot write auto ... and then the arg, because variadic PAGs are greedy. So it will take everything, and the last element wouldn't just exist, and that wouldn't compile either way because variadic PAG has to be at the end. But we can do something else. If you take a look into the comma expression like that, if you have 1 to 3, the outcome of that operation will be actually 3 because it will be the last element after the comma. So if you generalize that a bit more, the last element we can easily get out of a fold expression when we have ... comma args. So that will be equivalent to the previous example, 1, 2, 3, and we'll get the 3. That will give us also a warning that is unused value, warning that we don't use the 1 and 2. We can work around that by just assigning args to args on its own. Don't try it at home, but you can do it. That will silence the warning for us, and we'll get the value which we want. So that's still, we are C++, so we print using shift left operator. So that syntax is not as bad, I'd say, yet for our standards. We can still deal with that. If you want to get the first and last element, that's also possible. We just have the structure bindings from C++17. We'll have the immediately invoked lambda. We'll get the first element out of the function, and we'll propagate the rest to the fold expression. And in that case, we'll return a tuple from the first element, and the last element will be from the fold expression on TS dot. So that will give us the 1 and 3 in that example. So I hope that's still clear. There's no that much magic involved yet. We'll get into more details, more magic later. So that was about basically what can be done in C++ 2023 at the moment, and it's kind of simple. The future actually is sort of exciting if it will be approved. There's a proposal, structure bindings can introduce a pack. I think it's quite neat. So that will allow us to use structure bindings to get the first element in the following form. We have the structure bindings, we do first and dot TSS. You have to put a name here. We cannot do the dot, but we'll get the first. So that will be 1. What is exciting is that it's symmetric. So if you want to get last, we just do dot and then the last. So that will return the free. So in that regard, it's quite neat, I'd say. But what is even more cool about it is the fact that we can get the first and last at the same time. So you have first dot, that will go up to the last, but without the last, and then we have the last. So that will return the first and last being 1 and 3. So that's super cool in my opinion, because that opens a lot of abilities to approach. So to use the structure bindings to get kind of nth element. We could easily do that with that approach too. So that was about the proposal to get the first and the last. It is not an easy way without a bit of TMP on top of that to get actually the nth. So that's the discussion which we'll get into right now. So nth pack element. So the idea here, just to clarify again, we have a variadic pack, meaning we have something with the dot, and we would like to get nth element out of it. So if you have 1, 2, 3, we want to take 0, 1, or 2 in that case, which will correspond to 1, 2, and 3. Which is exactly that syntax. So we have nth pack element, we grab the n in the angle brackets, which will be the number, and 1, 2, 3 is the variadic pack which is introduced here. So the goal will be to be able to implement the tuple get. We will have our own simple tuple, and we'll implement the get. And in that case, the get will be implemented using different approaches, which we'll explore here with the different solutions. And nth pack element will be applied with the tuple here, and see how that can be put. We'll see whether we'll get better than the std tuple, or whether there are better approaches than std get, and maybe why. Okay, so the goal. As I pointed out, nth pack element returns element at the n position from a variadic pack. Nothing new here. Requirement. So we have to be able to get the nth element out of it, and that's nothing special. It has to be type agnostic. So that's the main reason why we're actually doing that. Tuple can have different types. So if you have different types, you're going to be able to take nth element out of that pack as well. So in that case, when you have a, which is a character, we want to return the character and not an int always, because it's not a common interface in that case. And also we would like to have nice error message, a kind of concept not satisfied if we try to get out of range, meaning if you have 3 elements and we try to get the third one, because it's 0 in text, that should fail. It will fail at the moment in std tuple. You probably have noticed if anyone tried that after 50 pages of error messages. Okay, so objective. we will compare different solutions, so we wanna kind of be able to judge them. Flexibility will be judged by the fact whether it supports different types. We'll have one solution which will not, but it's kind of nice, so I wanted to hint to it because it will lead into the final solution, which we will see. Readability is important, right? Because although the interface at the end is std-get or something like that, or env5 element, we want to understand that code, and we want it to be, beautiful code is simple, and vice versa, and we want to be able to understand because the code is much more often read than written. So in other words, how much magic is involved, and some of the solution I can immediately warn will have a lot of magic, TMP magic. Performance, is there any overhead? Not really a runtime overhead because all the solutions are, at compile time. We verified them with static asserts. However, there's an overhead if it comes to compilation times, and that's what we actually will benchmark in the end. Some of them are much faster than the others, and some of them are really bad. I would really encourage, since this talk is not really interactive, I can't ask the audience, sorry about it, to guess and try to guess which solutions will be faster than the others, and see how good your intuition is. I got everything right first time. Just joking. I was kind of surprised by the results. So maybe you will be as well. So solutions, there are three types of solutions which I split them into. They're probably different as well, but those are kind of common and have special properties which are important. So the first one is kind of using the function overload parameters. So we have a bit of magic to get n-1 element before the nth element. So somehow we get to that, and then we discard everything afterwards and return the nth. So that will be the first type of solutions which we will try to find ideas for, and that will give us the nth element using this approach. Another approach which is also pretty neat is the fact that we create kind of a magical, and here the magic is just nothing C++ related. It's just something which we'll have to put in. That's not valid C++ code. So in that magic, we'll create a struct or something which will have IDs mapping to types or values, and then we'll try to use inheritance or something, other tricks, to get back to that type ID based on the number as an nth element, so that we can return the object. I hope that will be more clear as we get to that. And the third type of solutions, because we'll take a look into different languages and different C++ languages kind of as well, and extensions which are capable of helping us with getting the nth pipeline. Okay, so what kind of solutions we'll explore? std array, just to see the syntax. Recursion, just to see whether that's good or bad. Arc expansion and the concept expansion to see how we can do that. We will use boost MP11 to see how that compares. Especially for everyone, I spent almost a day trying to get the preprocessor to work in order to show how that works. It's possible solution. Language extension we will compare will be type, pack, element, with Fluid Dion implementation in Clang. Circle, the newcomer. I'm a huge fan of Circle and Sean, so definitely something to show. And also the generalized pack declaration and usage proposal, which kind of applies Circle into C++, and that's also exciting. I don't have implementation for that because it's not ready yet, but we'll see how Circle implementation compares into other solutions we will have, so that we will get the gist how C++ can evolve in the future. Okay, so as I pointed out, there are always codable links provided, so feel free to verify them. So the first idea, and we always started with the same interface. We have nth-bug element with args.dot, and then in that case we verify that we have enough. But in the array example, which is limited because it only applies to the same types, we would create an array, and we'll just use index operator to get nth element. I think that's something which I really like about this solution. Therefore, I wanted to hint to it, because we'll get to something similar in the future, is that the syntax is something which we actually like, because we create an array with the ... and just index operator of n. And that seems to be simple to me, at least, and others, and I think that's close to the ideal syntax. But it doesn't work with different types, so we cannot really apply and compare that with other solution. So that's not great. But the readability, I think it's easy to follow in comparison to other solutions, and it's quite neat. Language features, so I would assume it's really fast to compile, because there's not much to do with the index operator here. Okay, so let's get into the proper solutions like recursion. In order to do that, and that will be the code will be in C++20. We'll use concepts and other things, but I believe all of the solutions, besides the one which is using concept, which we'll see in the future, are capable to be implemented in C++ 11, I guess, with the Varadic bugs. So at bug element, we have the case for the n equals 0. We just return the arg, because that's the arg which we actually want. Because if it wasn't the one which we want, we recursively gone again with n minus 1. I thought that's like a naive, understandable solution, which everyone starts with when they learn how to meta program in C++. But just to revise, we have the overload on the bottom as a starting point. We get because we have n greater than 0, assuming, and then we just go down and down and down, and we recursively call the same function, and at some point we'll get to overload, which is where the n equals 0, and we'll return the arg. So that's it. That's where we start with the naive solution. It satisfies our requirements, meaning it works with different types. It's flexible. I'd say it's readable. I think.
Which phone number, contact, or device do you want to call?
Sorry about that. It's readable. It requires a bit of magic for the final case with the n equals 0, because we have overload.
Contact or device do you want to call?
Sorry about that. So performance, is it slow or not? I would encourage everyone to guess, because it is different than other solutions in regards of the completion times. Whether it's good or bad, I don't know yet. I will see. So I just wanted to compare to a different recursion solution quickly, where we don't have a different overload, but we have if const inside. So whether that will be faster or not, I will leave that to you to figure out. Now I will figure out. I will show you the result later. But the idea here is the fact that we still have the same function, and instead of having a different overload, we just have one function with the different calls to itself. So whether that will be faster or not with if const and why, that will be interesting to see, in my opinion, because that kind of leads to whether should we write more overloads or should we write less overloads with if const if that's available, and that's in C++ 17. So what about this recursion? A second part Yes, it works with different types. Yes, it's readable. A bit of magic again. Well, performance, a hint here is less overload than recursion, but whether if context is more expensive than overload, we'll see. And the next solutions will always use the following trick, which is available with C++20, immediately invoked function expression, in which we have a lambda which we call immediately and expand on, in that case, ISs, which are the number, and then we use fold expression to expand on the call. And since the expression doesn't depend in that case on the ISs, in order to expand it, we just use comma operator with the void in order to be able to expand, because expression on its own can't be expanded. As I pointed out before, this proposal and the structure bindings will make that actually much easier. So we'll be able to do make index sequence, which is what we actually used before as well. Get the structure bindings, and just call the expression with expansion. So keep that in mind, and that's a blue background, something to remember. I think it's a very commonly used pattern in C++20 with tuple metaprogramming. So in our case, what we have is unroll function. In order for the performance reasons, we don't want to do the jumps and loops, and that will expand into two calls to the std puts without any jumping back. So that's pretty cool. A trick which can be easily applied. Okay, so moving to the solution which actually leveraging that approach. We have the lambda, nothing special here, just explain that. And then we do this trick with the function expansion of the parameters. So notice here we have this decal type, void start ns. What will that do is that will expand on ns times using void start. So what we will get here is void start, void start, void start, void start, ns time. Then we get the nth element, which is the one which we want, and then we ignore the rest. And we use pointers because void is something that we actually leverage here, and we cannot reference to the void. So we propagate the pointer to the args, that will expand, we will get the nth, return the the reference out of it, and we get the element. So that's kind of neat trick which we can approach. Apply and get the nth element out of the variadic block. It satisfied the requirements. I'd say it's in the spirit of Dharma magic a bit. We have to understand a lot of trickery of C++, but let's put that aside. The talk is about figuring out what's the fastest, what the options are. So yeah. We always hide it by the API. That's why we have std_get, because we don't have a language feature. Is it faster or not? Something to answer. There's no recursion involved, so recursion maybe it's slow, maybe it's fast. I don't know. Similar with C++20, we can apply somewhat similar concept with actual concept. We have a type and we have an auto as a parameters for the concept, which is called prefix in that case, and it's always satisfied. And we use it only for the expansion part. So the reason why we have this concept is to avoid this void start trick which we had here. So here we have a decal type of void start ns ... But you can imagine with C++20 and their syntax, we could actually implement it a bit differently by having a concept and then an auto which will expand on the concept itself, which will be the same outcome, however, a cleaner solution without pointers. So how does it look? We start with the same thing. Have the immediately invoked function expression, and then here is the magic, which is a bit less magical than the previous solution. And the idea is here that we have the prefix of ISs and auto dot dot, and that will expand IS times on the using the third syntax of the concept. So the first thing is the prefix of the concept, which will be satisfied always IS times, and that will be expanded until IS will run out, and then we will get the arc and then everything else. So if you pass the arcs to that, we'll get everything matched into the prefix IS times. Then we'll get the arc, which is the one which we actually want to get out, and then we discard everything else. So very similar to the previous solution, just a bit cleaner because C++20 allows us to do concepts here. So requirements satisfied, nothing special. Readability, well, I would claim a bit better than the previous solution. Still far into dark magic territory, I'd say. It's still faster or slower, hard to say. Doesn't use the recursion. Whether it's faster than the previous one, I think that would be interesting to answer. Whether the trickery from previously C++, previous C++ versions is better than the concept. There are a lot of talks about concept improving compilation times because we don't have to use SFINA. Substitution failure is not an error. In that case, it's not that similar, but we have a comparison between something which is a concept and something which is not a concept. And maybe one of the other is actually faster. Okay, so what about library solution? We have MP11. I would ask who is actually using it, but I see everyone. Oh, I have a note from someone that I made a mistake on the slide. Slide 35. Slide 35 was an arrow using an arc instead of arcs, a question mark. I don't think it's an error here. So just to go through, here we have the arcs. We propagate the arcs here, and we return an arc, which is the nth element. And that arc is being expanded towards ISs of number, like an IS number of previous parameters, then the arc, and then slide 34. That's where I am. So I think there's no mistake here, but if there are more concerns about it, feel free to ask me afterwards, and I will try to follow through with the explanation, or maybe there is a mistake which I just simply don't see. But this code might be checked on the Godbolt, so I would assume it was copied properly. Okay, I see. So the question has been answered. The mistake hasn't been confirmed. Okay, so MP11, everyone probably who is using Boost and TMP knows about it. It's quite a neat library from Peter Dimov. It's really fast to compile, one of the fastest if we check on the meta bench of TMP stuff. So it's pretty cool. Whether it will be fast, in our case, we'll see. How we approach it. Here, everything is in Boost MP11 namespace. So we can take, and the approach is the same. We take nth elements of the list. So we have a list of arcs. We take n of them. So that we can actually expand into the TSS here. So it's very similar as the approach to what you had before with the void, after that with the concept. Right now, we actually say take nth element before the arc, expand over them. That will be the TSS, because now we know exactly what that will be, and then get the arc, and then ignore the rest. So the idea here is very similar. The main difference is that we actually know the nth element types, and we get the empty list of them and expand over them. So whether that will be faster or slower, I think it will be interesting to see. readability on its own of that solution, I think, is a bit better because we actually were able to hide a bit of magic into the library. Unfortunately, a lot of it's still exposed, but we can argue whether that's a step in the right direction. Definitely, it's a bit better, in my opinion. As pointed out, MP11 is well optimized for compilation times, so maybe we could assume it will be good, but how it compares to the other solution, we'll see. Okay, I know everyone who is watching that was waiting for that, and that's why you were joining this talk. Let's take a look. Boost preprocessor. Yes, as I pointed out, it's something which probably we want to use in production. However, it has very certain properties which are interesting to see. So the approach and the idea is quite simple. We have the generation of the code happening for the different elements. So in that case, we have, if the I equals 0, that means that that's our element. We get the arg and we dispose everything else. If the I equals 1, we ignore the first one and get the second one and return that one and ignore the rest. And if I equals 2, we would have auto to ignore 2 and get the third one and ignore the rest. So how to do that with Boost preprocessor? Just for the record, I wrote this code and it compiled the first time. Just a disclaimer, no, that's not true at all. But I tried. So that's where we start. And that's, let's take a look into that, what's happening here. So we have the macro, and we will use Boost preprocessor, Boost pp repeat, which we will repeat n times. That solution is coupled by the number of possibilities in the Boost preprocessor, which I think it's 256 or 1024, depending on the Boost version. So it will be limited. And what is really interesting about that solution that we will compile in all the overloads up front, because we have to say the number up front, how many we actually support. And in that case, it's Boost pp limit repeat, which is, let's say, 256. So if we actually ask for the first element or the 200, the compilation times will be very similar in that regard, because we'll have to compile all of them up front either way. So I was thinking that would be interesting to see how that compares, because we will do work up front, a lot of work up front. If you want to get into details of that one, maybe poke me afterwards. But the idea here is that we Boost pp repeat, Boost pp inc is to increment, hash is to join, and we generate the code which was provided before. And Boost pp limit repeat times. So we always try to put auto n times before we get the nth element, and I'm n minus 1 times because after we get the nth element, and then we ignore everything else with the auto. Okay, we passed that through. Sorry if that was unclear. I wouldn't advise anyone to actually use that, but maybe the library authors may learn something out of it. So readability, it's it's preprocessor text replacement. Error messages will be terrible. It won't be hinting even to the right place in the first place, and it won't be great. And it's obviously hard to read because I don't know, it's just preprocessor, so everything is difficult because we don't really see the code which is actually generated. So how that compares if it comes to performance, that'll be something we'll see later. As I pointed out, there are multiple overloads precompiled in that case, so maybe it would be good for like precompiled headers or something, but that's the solution which you have. Okay, so let's dig into some other solutions, how we can get the nth element so that we can compare them. In that case, we'll get a struct, and then we had this concept before. in that case, we'll have a struct because we'll try to have a different approach in which we will do the immediately invoke lambda, and then here we'll create an anonymous struct. That's why we don't have a name. We get the any of the type and the element. We inherit from them, all of them. So the struct will inherit from all the pairs, kind of. Any is kind of like a pair, but we don't have universal template, so we have to have any which takes the T and author. But you can leverage, like, imagine that's a pair of type and ID. We create that object because we want the value, and then we will just try to get the one. We'll leverage inheritance here to get the one which is associated with the n. So the n is coming from here, from the call itself, but the t will be deduced accordingly to which n is associated to the t, because we inherited from all of them, and only one can match in that case for the given number. So the one which will be inherited from and matching the n and the t it will be deduced and return the t value. So that's one way of doing that as well. And the struct is anonymous here. Some people pointed to me that's a really weird syntax. I kind of agree. It's kind of weird, but that's C++. Okay, so requirements satisfied. I'd say it's very magic. It's even more magical probably than the previous solutions, because it's like we cannot look at the overloads themselves that easily. There's no recursion here. There's no much with the overloads and parameter expansion. So maybe actually that will be fast. Maybe it will be slow. Okay, quickly let's go through the language extensions. Type element is something which Clang has. And we can, it's really great for the types themselves. So if you have the Varadic pack of types and you want to take n, grab n out of it, that would be very easy with that solution and really fast. And that's like how I believe as MP11 outer library leveraging the approach in Clang. But in that case, the only difference is that we do not use the inheritance to get the nth element, because we can actually get the nth element out of this variadic pack and then static cast to the proper type, which we know the type of, because we've just found it out by the tuple pack element, type pack element, which is great for the variadic pack. So this guy will return us the proper any with the given type and given number, so we can static cast it and return the value. So I hope that's similar to the previous approach. Hopefully that's clear enough. Is that flexible? Yes. Readability, well, it requires an extension. It doesn't work with different compilers, so it's a bit of knowledge burden. But I would say, like, my assumption would be that it will be fast because it's a compiler extension, right? It's feature in the compiler. Okay, we got into the Circle, which is the C++ compiler implemented by Sean Braxton, and it's really powerful and has a lot of extensions. Sean is working on a lot of things right now, Rust related in Circle, but in my opinion, it's the best TMP powerhouse for template metaprogramming, way better than C++, and a lot of approaches are related to the Circle, which might be in the C++ eventually. So that's what it is in Circle. We get, like, I hinted a bit at that with the array. It was very close to ideal syntax, in my opinion. I think that's ideal syntax. There is not much else we can, shave out of the syntax here. We just get r_that of n. Like, that's expressive. That's what we want. And it's a compiler feature, so it will be fast if it's implemented right? Yeah, I think it can be easier, but it's not C++, it's Circle. It's a language feature. I would assume it'll be fast. So moving to the pack declaration, that's also possible with the proposal P1858. It's the same syntax, it's the same code. If you get that proposal, yes, please, that will be the thing which we'll be able to do. And it's as good as Circle. Yeah, another guess because it's the same. Okay, so how we can implement the get, just to hint why we have the get as a free function of the member function, why we don't have .get. It's because we would have to put .template for use cases where we have a dependent context. So in order to avoid when you have t.get, and we would have to write t.template get, which would be probably even more magical than anything else, we would have to, the committee decided to get std_get as a free function. Okay, so that's the tuple. And right now, the simplest tuple in order to implement our use case will be just leveraging lambda expression. So we have a tuple which takes the TSS, and TSS will be applied via a function, like a functional programming for the tuple. And that will give us really leverage for the nth pack element function. So our get equivalent to std_get will look like that. We have the tuple, and we get the expansion over args, and we get the nth pack element of the args, which we discussed many times so far. Quickly, bonus, because I want to get to the benchmarks. With C++ 14, I guess we can get actually much better tuple interface with 0, 1, 2. We don't have context for parameters. We may never have them. So _c is something which creates, it's a UDL which creates an object, like integral constant of 0, 1, 2, 3. And then we can easily apply n _c for the given element, and that will call the index operator, and we avoid all this .template magic because it's reduced. So how to implement that? And that's the whole implementation. Notice here the auto n here on like in the middle of the screen here. It's not an int. It has to be integral constant type, so that we can apply it here because we don't have context for parameters. And how to get the _c for the number? We just parse, like C++ 17, I think, or 14 introduced the UDL for the characters, like generic, and we can get the number of it. So 42c _c will create a 42, but it will be an integral constant, which we can propagate through the parameter and get it applied to the std_get in that case. Okay. Circle. That's the tuple in Circle. Hello. C++ wake up. No unique address. TS.dot. Get is just here index operator ts.n. If you get that proposal, that will be our tuple plus all the 100 constructors we will have to implement on top of that. But the simple version, that will be it. Just quickly, tuple manipulation. It's kind of showcase what can be done with C++ 20. That we can manipulate tuple with ranges. It's not really important. It's more an advertisement than anything else at that point of presentation because I don't have enough time. But the idea here is that we can apply the std ranges to get tuple manipulations and typeless manipulations with ease, in a sense. So, for example, if you have ranges, we can get a tuple, we can filter, reverse drop, and that might be applied using this library. And then we can get the static assert, notice here, not the static assert, where we get the tuple manipulation of values, and we can do the same for types as well. So that could be a MP list or anything like that, and that could be applied the same way. Okay. Always measure. If it comes to benchmarks, the intuition is never good enough, and always measure in a production-like environment because micro benchmarking might be misleading. So readability on its own, all solutions have some sort of dark magic. I would say only Circle and P185 is worth looking at from the readability perspective. Performance, we have different use cases. We either have a lot of tuples with less than 20 elements, or we have a big tuples with more than hundreds of thousand elements. The second is something which is often applied in HFT because we have a lot of types which we want to, for parsing, which we want to apply, and we will have a lot of big tuples. So we care about the completion times. C++ limitations at the moment are counting thousands, so we cannot have tags for million elements, which some may imagine, some may not, but the limitation at the moment is thousands. How we measure the performance, we get the meta bench from Louis to get it measured. It's like Ruby-based thing which generates the code for us, so we can actually measure the compilation times, memory consumption, and stuff. Encouraged to use. So the numbers. I measured it for GCC 12 and Clang 15. So as we see here, like for elements below 20, it's sort of similar. Recursiveness is not ideal. What's interesting here is that the recursiveness 1 is slower than recursive 2, which I was kind of hinting to the fact that overload resolution is slower than ifcon's-expr. So that's one finding. Other findings is the fact that the fastest solution are arc expansion, apparently here. GCC doesn't support Clang expansion, concept expansion, but we can see that preprocessor is slow in comparison to MP11 and arc expansion. How that compares to Clang, kind of similar. Recursive is slow. We don't really care about that. Also, preprocessor is slow. And then we get to better numbers for like 200 elements. On 20, it's kind of hard to measure because there's a lot of noise and only the obvious solutions are out, like recursiveness. But for the bigger pack, we see that the concept expansion is actually the fastest. So the expansion over concept is interesting. What is Circle interesting about is that it's very similar. Recursiveness is slow, but what I wanted to hint towards, like all other solutions are somewhere, and that's the circle here on the bottom. It's just flat, basically flat. It doesn't matter how many elements, it's flat, and that's what we should strive for, in my opinion. That's like the main outcome of this talk. So what are the highlights here? For small numbers below 20, it's a lot of noise, so there's no clear winner, it's just clear losers, like recursion, a lot of noise. Recursive solutions don't scale well. Multiple overload slower than ifcon's-expr, that's proven as well. That's something which is maybe worth taking into your code. Clever solutions scale quite well in that circumstances for the NFAG elements. So if you get fancy, we're good. Circle approach as a language feature approach is something which just destroys the competition. It's flat, no matter how many elements we have. It's much faster on its own. There's like basically this talk doesn't make sense if you just have Circle. And if you have Circle, we may get it actually by P1858. So fingers crossed for that one. So how that compares to tuple, a very similar result. Recursiveness is low. and the fastest is actually STD tuple. So that's really interesting. GCC 12. That for 20i I can't say, but for big elements, STD tuple is even faster in GCC 12. So well done. They have even better solution. For Clang, on the other hand, and for GCC 11, that wasn't the case. So when I updated the talk, they got better. So maybe I had some influence towards that. And here we also have STD tuple as a top, which is great, meaning the different approaches are applied, which are even faster. What about Circle? Circle is also interesting because I don't know. I don't know whether you see the number, but it's basically 0 for Circle, and tuple is the closed with MP11, and direct expansion generally close. But there's no comparison since Circle is so far ahead. So again, recursiveness is low. Clever solutions are okay. GCC and Clang STD tuple is pretty good. Yeah, it wasn't the case for Clang before Clang 14 and for GCC as well, for GCC 11. So it has been a huge improvement. So if you can update, that would be a good thing for the compilation times if you apply the tuple. And Circle approach to tuple as a language feature destroy the computation. However, Circle is using libc C++, so on its own, the tuple is slower and is not as fast as Circle tuple implementation. So that's why the number for Circle here is for tuple itself is really much slower than for Circle because it's libc C++. But potentially, if the tuple will become standard, then that would be much faster, like the tuple as a language feature. What is also important, which I wanted to hint lastly here, is the fact that there's something wrong with our compilers, because GCC and Clang are much slower than Circle. If you compare it to the best solution and the worst solution in a second, notice here, like GCC is slower than the Clang, but they don't compare even to Circle, and the same for the tuple, and that's for best solution, which was Circle in that case. So maybe that's not fair comparison. But the worst solution, which is the recursiveness part of it, it's still much slower in GCC and Clang, and GCC compiles slower than Clang, but like 5 times slower than Circle. So we have a lot of things to do still in order to compilation times in GCC and Clang, because Circle just can't do the same thing much faster. And how does it compare to different languages? Quickly here, I compared dlang, Rust, Zig, Circle, and Clang. So below 20 elements, it's kind of okay. Everything seems to be similar. There's a bit more overhead to start with D and Zig, but pretty much it's the same. But what is interesting, above 100 elements, is that's Clang. It doesn't scale very well if it comes to tuple std-get in comparison to any other language. It starts pretty well, but it doesn't go too far. And Circle is here, like you can't see it because it's on the bottom and it's on the black line. So just to sum up, since we have just 1 minute, readability. Clever solution should be hidden behind test and user-friendly interfaces. I think that's kind of obvious because we don't want to, see the dark magic in front of us on daily basis, unless we work in HFT or similar. Performance, recursion is slow. I think that's nothing really new, but definitely do not apply naive solutions if you care about compilation times. Circle pack manipulations are super fast and scale well, and that's something which we want. And I believe strongly that lack of language features to manipulate And store variadic pack is hurting C++ quite a bit. And if we get the P1858, that'll be much easier and much faster. And C++, moving back to the why this talk actually happened, would benefit even more and would be able to outpace in a space of the max performance other languages, where I think C++ should go to, because other areas are kind of taken by the new languages at the moment. So with that, yeah, let's pack some more language features, and thank you very much.